Pumping bicycle tyres can be hard work, and I use the word work in the scientific sense. Now my intention is simply to compress the gas, but if I keep pumping for any length of time, the pump gets hot. So some of the mechanical work energy going into the pump is appearing as thermal energy. This suggests that there's an intimate link between work and thermal energy, and as you know, the study of this link is the province of thermodynamics. The principles of thermodynamics underlie the operation of all practical machines. Now you might not have thought of it before, but this electric kettle is a machine. It takes in work in the form of electrical energy and heats water. That is, it acts as a converter of work to thermal energy. Here's another machine. The domestic refrigerator. This again takes in work as electricity, but this time transfers thermal energy from the inside of the fridge to the outside, the opposite of the kettle. Now, despite the complexity of many machines, they're all governed by the same thermodynamic principles. So we're going to demonstrate some of the concepts of thermodynamics introduced in Unit 4 and show how they're used in some practical applications. Let's start by introducing the idea of a thermodynamic system. That is, some region of space which contains all the materials we want to examine. It's surrounded by a closed surface called a system boundary. Everything inside the boundary forms part of the system. Everything outside the boundary is known as the system environment. We then aim to describe the behavior of this thermodynamic system by monitoring or describing the transfer of energy and occasionally materials across the boundary. Now the system can be chosen to suit yourself. For example, if we wanted to describe the performance of a bicycle pump, we could imagine the boundary as lying along the outer surface of the cylinder. In this case, the metal of the cylinder would form part of the system. Alternatively, if we wanted to describe only the behavior of the gas in the pump, then we'd choose the boundary as lying around the inside surface of the cylinder and piston, and now the metal part of the pump is excluded from the system. In this case, when I push in the piston, work energy is being transferred from the environment across the system boundary to the system. At the same time, you'll notice that the volume of the system is getting smaller. So the system boundary doesn't have to be fixed in space. But what about this? If I choose to define the system boundary as lying around the external surface of the kettle itself now forms part of the system. The energy input to this system is thermal energy, transferred from the hot gas flame across the boundary, here the base of the kettle. The energy output from the system is thermal energy, mostly as steam from the spout, but also that lost from the surface of the kettle itself. But in this instance, there's also a change in the mass of the system, because water's lost as steam through the spout. So this could be a much more complicated system to deal with than simply heating cold water. An alternative thermodynamic system that could be used to describe this would be to define the boundary as enclosing all the water initially present in the kettle. In this way, the mass of water in the system is constant, but of course the system boundary would change shape and size as the kettle boiled, so that it always included all of the steam given off. You should get used to the idea that thermodynamic system boundaries don't necessarily coincide with the walls of physical objects. However, having said that, it's certainly true that whenever we try to describe the thermodynamic properties of practical systems, the system boundary frequently does lie along some physical surface. Take a familiar object like a house. To describe the overall thermal properties of this house, we could define a boundary lying on the outside of the walls and roof. The energy inputs would be thermal energy as radiation from the sun, plus any work energy taken from the main supply. The energy output would be the thermal energy transferred from the inside to the outside environment. Well, that's okay for a house, but what about a car? To describe the overall performance, we could define the system boundary as an envelope which encloses the whole car. On the other hand, if we were interested in the work that could be derived from the engine, then maybe we should define a system to enclose only the engine. A more useful and simpler starting point, however, might be to consider not the performance of the whole engine, but to examine the performance of a single cylinder, and a system would then be defined to enclose only the gas in the cylinder. Well, let's have a look at how a gas in a cylinder behaves. We're going to consider two systems of a cylinder and a piston. Both cylinders contain a given volume of gas trapped by a piston, but there's a difference. The right-hand cylinder contains a conducting object, a metal, to allow thermal energy to escape or enter the trapped gas. The volume of gas is recorded on the left, about 80, and any temperature change is recorded on the right. The pressure of the gas can be varied by placing weights on the piston. The left-hand setup is identical, except that this time, instead of a conducting outlet at the base of the cylinder, there's an insulating object of the same volume as the metal one, going up to about 20 on our volume scale. So this time, no thermal energy can escape or enter. The volume of gas is again measured. It's about 80 now, and any temperature change is recorded by the meter. What we're going to demonstrate now is the difference between a change in which no thermal energy can escape and a change where it can. First, the insulated cylinder. And we can see that as the pressure is increased, the temperature rises. This is called an adiabatic change. Now let's see what happens when energy can escape. The temperature hardly changes. If the process was slow enough and the walls were perfect conductors, we'd have a change at absolutely constant temperature. This is called an isothermal change. So there are two quite distinct types of change that can be caused. An adiabatic change, that is one in which no energy is allowed to cross the system boundary. In adiabatic changes, the temperature of the system invariably changes. Then, an isothermal change is one which takes place at constant temperature, and there's invariably energy transfer across the system boundary during such changes. Now, when we supply energy to a thermodynamic system, the system doesn't distinguish between an input of thermal energy or an input of work. It treats them as equivalent forms of energy. The first demonstration of the equivalence of thermal energy and work was carried out by the 19th century physicist Joule. His original apparatus is now in the London Science Museum. What he did was to use a paddle wheel in water. He showed that by rotating the wheel using mechanical work, he could produce a rise in temperature. We can demonstrate this more generally with a more modern experiment. We have three identical metal cylinders. To the first, we're going to supply thermal energy. The second, we're going to do work on it by rubbing the surface with a cork. This is equivalent to supplying mechanical energy. With the third, we're going to pass an electric current through a heating element. Okay, let's switch on and see what happens. All three cylinders are registering a similar rise in temperature. By picking our parameters carefully, we've been able to produce the same temperature rise by supplying either thermal energy, or mechanical energy, or electrical energy. This equivalence of different forms of energy is summarized by the first law of thermodynamics. Which simply states that the state of a system can be described by an internal energy. Any change in internal energy is the sum of any thermal energy put into the system plus any work energy put into the system. Essentially, the first law of thermodynamics is nothing more than an expression of the law of conservation of energy. We can transfer energy from one place to another, but we can't create or destroy it. Now, internal energy is a state function. That is, if the temperature, pressure, and so on of a system are defined, then the internal energy is defined, and it doesn't matter how the system got into that state. However, when we want to change the state of a system, it does matter how we do it. I'm going to increase the pressure on this cylinder very slowly, and we'll follow the changes in pressure and volume on the oscilloscope. We see the pressure on the vertical axis going up, and the volume on the horizontal axis going down. Okay, so let's store that and reduce the pressure again. We can see almost exactly the same path is retraced. The work done in compressing the gas is the same as the work recovered when the gas expands. This process is therefore a reversible process. Let's now put the same weights on, but all at once. This time a loop appears. Let's see that again. This loop means that more work was done in compressing the gas than was recovered when the gas expanded. This characterizes a non-reversible process, and it means that work energy had to be supplied to take the gas round the cycle. So reversible processes usually involve extremely slow changes. Fast changes are invariably irreversible. So when we talk about reversibility in thermodynamics, we're not just talking about returning a system to its original state. We're talking about being able to return a system to its original state without doing any net work on the system. Now, the reason we're interested in reversible processes is that they're the most efficient changes we can cause. That is, they require the least expenditure of energy, in that all energy put into the system is potentially recoverable. Now, why is this important? Well, as I said at the beginning, we're interested in machines. One of the simplest types of machines is a heat engine. Essentially, such machines contain a working fluid, such as a gas in a cylinder. Thermal energy is transferred to this working fluid, thus increasing its internal energy. Some of this energy is extracted as work, so that the fluid is returned to its original state. In this way, the fluid is taken around a cycle. The simplest type of cycle is the Carnot cycle, which employs only reversible changes. Compression is in two stages. The first stage of compression is isothermal. That is, energy transfer by heating occurs at constant temperature. The next stage of compression is adiabatic. No thermal energy transfer. The fixed mass of gas is now fully compressed. Expansion also occurs in two stages. First, isothermal. That is, thermal energy transfer with no temperature change. And finally, adiabatic expansion to bring the gas back to its original state. Let's see what this means in terms of the familiar PV diagram. Isothermal compression, compression along an isotherm. Adiabatic compression, temperature increased to another isotherm. Isothermal expansion, expansion along this upper isotherm. And finally, adiabatic expansion to bring the temperature back to the original isotherm. And so on. And this area of the PV diagram represents the net work done during a cycle. Now, the Carnot cycle is an idealized engine, but this is a real engine, also using a closed mass of gas as a working fluid. It's called a Stirling engine. and at Reading University, Dr. Graham Rice is interested in it, both for teaching and for applications.
Stirling engine converts thermal energy into mechanical energy. Gas is kept hot during expansion and cold during compression. The engine has the following basic components: a cylinder containing a working piston or power piston, a displacer which divides the engine into a hot space and a cold space. The engine is heated at the top and cooled at the bottom. The engine is fitted with transducers which enable us to examine the way in which the pressure varies with volume during the cycle. The lower curve represents the compression process. With volume decreasing, the pressure increases. The upper curve represents the expansion process. As the volume increases, the pressure falls. The area of this diagram represents the work output during a cycle. We can now stop the engine to examine in more detail the sequence of events during the cycle. The engine has a power piston and a displacer. In this case, the displacer is made of glass and has a passageway which connects the hot space to the cold side of the engine. The passageway has porous copper which acts as a heat store, which is called a regenerator. With the power piston and the displacer in their top position, the gas is contained wholly within the hot space. The gas is at high temperature and high pressure. The high pressure gas forces the piston downwards, which produces a power stroke. At the end of the power stroke, the gas is displaced from the hot side to the cold side by movement of the displacer piston. The gas gives up heat to the regenerator during this process. The upward movement of the piston causes the gas in the cold space to be compressed. At the end of the compression process, the displacer moves downwards to push the gas back to the hot space. The gas picks up heat from the regenerator during this process to complete the cycle. We now go through the cycle again with the PV diagram. With the power piston at the bottom and the displacer at the top, we have maximum volume, V1, and minimum pressure, P1. Power piston moves upwards to increase the pressure from 1 to 2, with the gas cooled to keep the condition isothermal. We then move the displacer downwards to force the gas from the cold side to the hot side. The gas is heated by the regenerator, causing the pressure to increase from 0.2 to 3 on the pressure volume diagram. Downward movement of the piston, representing the expansion process, 3 to 4. The pressure is reducing as the volume increases. Finally, the displacer piston moves upwards, pushing the gas from the hot side to the cold side. The gas is cooled by the regenerator to reduce the pressure from 4 to 1. This represents a discontinuous movement of the pistons, as shown by 1, 2, 3, 4. We have now been through the idealized cycle with discontinuous motion of the pistons. In the actual engine, the pistons move with sinusoidal motion to produce the PV diagram as shown on the oscilloscope. The work output of the engine can be increased by increasing the pressure of gas in the engine, which in effect increases the area of the diagram or increases the mean effective pressure on the piston. We can have a further increase in power output by changing the gas from air to a light gas such as helium or hydrogen, which is more easily pushed through the regenerator from the hot side to the cold side and back. This allows us to operate an engine at high speed, high efficiency, and high specific output. The engine has two major advantages. Firstly, low noise, because it has no valves, and secondly, multi-fuel capability, since the engine simply has to be heated.
Stirling engines were first used in a domestic context around the turn of the century, with air as the working fluid. Since then, various rather expensive developments have been tried for use in road transport. But a new area of application has emerged in recent years, which exploits the fact that the cycle is based on external combustion, and so any convenient fuel can be used. For developing countries, an appropriate fuel might be rice husks. A firm called SunPower in the United States has been perfecting a machine based on burning these. This is for export to Asian countries.
This is a biomass burning hot air engine or Stirling engine using air as a working fluid. It's a very simple design intended for use in Bangladesh, India, Latin America, Africa, burning anything that's available, whether it be rice husks or corn cobs or straw or wood or lignite, anything. It works on the same principle as the standard Stirling cycle. That is to say, it has an external source of heat, which is used to heat air. There's a piston inside which moves the air back and forth between the hot space and the cold space on the engine. It has a cooling jacket just like a normal engine. And as the pressure rises and falls, it pushes the crank piston back and forth, and that generates mechanical work. This particular engine probably has an overall thermal efficiency of somewhat less than 10%, which does not sound very high, but actually it's a good deal higher than a small steam engine and not too far away from the efficiency of a gasoline-powered engine of the same size.
What's the theoretical efficiency of these Stirling engines compared with, say, internal combustion and steam engines?
The theoretical efficiency of any Stirling cycle machine is very high. It approaches the Carnot cycle limit. The actual achieved efficiency, of course, is always much less than that.
How does that compare with a diesel engine?
It's about the same for the same size. And since this is a very simple machine, it's not as good as a Stirling engine could be by any means. With a little bit more material costs, the efficiency of this machine could be much higher, say 25 or 30% without much difficulty.
An alternative application of Stirling engines in the Third World is in irrigation, where pumps may need to be located in remote areas. SunPower are testing possible designs using whatever fuel is handy.
And we think the overall productivity of the rice growing areas could be increased by this machine. Waste from the rice crop would be used to drive the water to irrigate the rice crop. So this, we feel, would be in some sense a breeder reactor. There would be far more fuel produced by the irrigating Stirling engine than is consumed by it. The major advantage of the Stirling is that it will use rough fuels, any fuel, anything that can burn.
So in this program, we've seen not only how the basic principles of thermodynamics are arrived at, we've also seen the importance of thermodynamic cycles and their applications to real devices like Stirling engines and in reverse mode devices like your own refrigerator.